First problem, cosine of theta equals 2/5. What we're going to do is draw that scenario. And for now, all the trig we have is based on right triangles, so we're going to draw a right triangle. Theta is our angle, so we're going to put a little mark on one of those acute angles. We're going to call that angle theta. And it says that the cosine of that angle is in the ratio of 2/5. SOHCAHTOA is our key as to what this is going to look like. In this problem, not all of these letters are important. We're dealing with the cosine equals 2/5, so these three inner letters are what matter. Cosine is adjacent over hypotenuse. In other words, the ratio of the adjacent to the hypotenuse is 2/5. Now, I'm not sure if this length actually, for my adjacent, is 2, or if my hypotenuse is 5. It could be 4 and 10, it could be 6 and 15, but the ratio between those sides is 2/5, so I'm just going to use those numbers. I could put 2x and 5x, but that really isn't necessary. So here's our triangle. In other words, this information we have right here is translated into that triangle. I know what that triangle is going to look like, or at least simplify it down to. And since it's a right triangle and I know two sides, that means Pythagorean Theorem would apply. In other words, leg squared plus leg squared equals hypotenuse squared. So 2 squared plus this squared equals 5 squared. Do some algebra on that, and then this length comes out to square root of 21. So just given that the fact that the cosine of theta was 2/5, I know that the other side then is root 21. Now I'll go to the question. The question says, what is the sine of theta? So from our reference angle, which is in this lower right-hand corner, we want the sine ratio, and that's the first part of SOHCAHTOA, SOH. Sine is opposite over hypotenuse. That would make it square root of 21/5, and that is our exact answer. I don't want to put a decimal answer for that. I want to give the specific exact answer. Moving on. Next one. Tangent of alpha equals 6/5. So this is another Greek letter for us. We'll use a few Greek letters. Primarily, we're going to be using theta. This time we're switching off to the Greek letter alpha. The tangent of alpha is equal to 6/5, and I'm asking you for the sine of 90 minus alpha. Once again, we're going to take this given information and translate it into a triangle, specifically a right triangle. I have my right triangle. Once again, I'll use this lower right-hand corner for our given angle alpha. It doesn't have to look like that. We could put the right angle somewhere else. We could rotate this around. We could translate it. This is just the way I'm preferring to draw this one. And the tangent of the angle is 6/5. Think back to SOHCAHTOA. TOA is what's important for this one. Tangent is opposite over adjacent, so the opposite over adjacent ratio is 6/5. My drawing doesn't look terribly accurate. The 6 doesn't look longer than the 5. If that's a problem for you, then you can redraw it and make it look accurate. But the important thing is I have the sides in the correct location. Unlike the last one, this time I don't know the hypotenuse, but I do have two sides of the right triangle. So again, Pythagorean Theorem applies. 6 squared plus 5 squared equals the hypotenuse squared. 36 plus 25 is 61. So this length is the square root of 61. So now we know all three sides of the right triangle, which is great. What we're being asked for, though, is the sine of 90 minus alpha. Well, alpha is this angle. What is 90 minus alpha? What is that? The relationship between this angle and this angle is that they are complementary. In other words, if this is alpha, 90 minus alpha is the other acute angle. So now we're changing our reference angle. Instead of using this as the reference angle to get a sine, cosine, or tangent, we want to know what is the sine of this other angle. Sine is opposite over hypotenuse, so from there, the opposite is 5. The hypotenuse is square root of 61. So there is the sine of that angle. I don't want to leave it in that form. I can't have a radical down in the denominator, so we will rationalize it by multiplying numerator and denominator both by root 61. So it's 5 root 61 over 61. Not exactly a pleasant looking answer, but There's no radical in the denominator. It won't simplify down anymore because the coefficients, the integers 5 and 61, don't have anything in common. So that is the sine of 90 minus alpha. Next problem, sine of beta equals 5x, cosine of beta equals 2x. So that gives us a right triangle that is going to look something kind of like this. We'll put beta in this lower right-hand corner. And the sine of that angle is 5x. That means the opposite over hypotenuse is in the ratio of 5x to 1. So the opposite is 5x. The hypotenuse would be 1. That makes it so that the sine of beta is equal to 5x. The cosine of beta is equal to 2x. So the adjacent over hypotenuse is in the ratio of 2x to 1. So it looks something kind of like that. Again, not necessarily drawn to scale. The 5x shouldn't look smaller than the 2x. If you want to fix that, you can. But here is our drawing. From this, we have 3 questions to answer. What is the tangent of beta? What is x equal to? And then what is that angle beta actually itself? Let's get to the first one. The tangent of beta is opposite over adjacent. So from this angle that we're dealing with, we would say that the tangent of beta is opposite over adjacent. So that is an answer, 5x over 2x, but we want to simplify this down like we would with any other fraction. The numerator and denominator both can be divided by x, so then we get that the tangent of beta is 5/2. So there's our start. Next one, we're trying to find the value for x. And there actually is a value for x in this one. We have a right triangle. We have 2 of the 3 sides in the right triangle. So that means, like a lot of other problems, we can use Pythagorean Theorem. In other words, 5x squared plus 2x squared equals 1 squared. And if I write it like that, it's not completely accurate because I'm not just squaring the x's, I'm squaring the entire quantity. So 5x squared, 2x is being squared, and then just the plain old 1 is being squared. If we start evaluating this out, it's 25x squared plus 4x squared equals 1. 29x squared equals 1. X squared equals 1 over the square root of 29. Oops, 1 over 29, but then we square root both sides. So x equals plus or minus 1 over the square root of 29. Whenever you're solving an equation and you take the square root, you have to put the plus or minus in there. Could x be negative? 5x and 2x are based on length. So if I plug a negative value in here, that means that the length of this segment is 2 times a negative, which would make it negative. So that actually doesn't make sense. Algebraically, plus or minus, but geometrically, according to this problem, it can only be the positive. So x equals this. Rationalize that problem, and we get that x is equal to root 29 over 29. The last thing that we're asked to find is beta. And this should have the approximate symbol after this. We can't get the exact value for this angle. Very rarely are we ever going to get an exact angle measurement. This time we're going to get a decimal approximation. What we know about this problem is that the tangent of beta equals 5/2. What's better about this tangent as opposed to the sine or the cosine is that there's no variable in this one. The tangent of beta equals 5/2. My goal is to solve that equation for beta. The inverse operation of tangent is tangent inverse. So if we take the tangent inverse of the left, it gives us just beta. That's how we can get to that variable all by itself. We don't divide, we don't square root, we take the tangent inverse. So then if you take the tangent inverse of the right, we get this expression, tangent inverse of 5/2. That can actually be solved on the calculator then. As long as we're in degree mode, we can take the tangent inverse of 5 over 2. The tangent inverse of 2.5 would be the same thing. And when you do that, you get that beta is approximately 68.2 degrees. And for angles, we're going to put all of our angles rounded to the nearest tenth of a degree then. We have the drawing of the triangle rather than given that the sine, cosine, or tangent equals anything. Our goal isn't just simply to find this unknown length, it's to find the angle measurement for theta. If I look at this drawing, it's a right triangle, so I could use Pythagorean Theorem to find this bottom length. There'd be nothing wrong with that, but it's really unnecessary. Instead, I'm looking at from this angle, and from this angle, 3 is the opposite, 10 is the hypotenuse. So we have to look and see, well, what trig function uses the opposite and hypotenuse? This is where SOHCAHTOA is relevant to us again. SOHCAHTOA, sine is opposite over hypotenuse. So I could write that the sine of our angle theta is equal to 3 over 10. That's what this drawing is indicating. It never actually said that, unlike some of the previous problems. Instead, we have to look at the drawing and interpret that. And now we know that, yes, sine of theta equals 3/10. From here, we want to get to the angle itself. So to isolate that theta, we'll take the sine inverse of both sides as an exact value. Theta is the sine inverse of 3/10. Use your calculator to solve this one, and that's going to come out to about 17.5 degrees. We can do a small visual check on this one. Sometimes the drawings aren't to scale, but the sine of theta is 3/10. If we use Pythagorean Theorem, we could get this side. This unknown side at the bottom would come out to square root of 91. And square root of 91 is a lot bigger than 3. This angle that we found, theta, is pretty small, 17.5 degrees, and it seems to make sense. Small angle, really small side. Bigger angle, bigger side. If I wanted to know this other angle, this 90 minus theta, I could take 90 minus this one and get about 73.5 degrees. So just kind of a quick visual check to make sure that that really is accurate. All right, here is our next one. This time instead of theta, we're using the other Greek letter again, alpha. Our goal is to figure out what is alpha approximately equal to. So we look at the drawing, and relative to that angle, we have to determine what is the 2, what is the 11, opposite, adjacent, hypotenuse, and all that. And then we have to figure out what trig function this pertains to. If I wanted to, again, I could use Pythagorean Theorem to find this side, but that's just an unnecessary step because I have enough right here to determine the trig function. From this angle alpha, the 2 is the adjacent. From the angle alpha or any other angle, 11 is going to be the hypotenuse. So we want to know what is the trig function that relates adjacent and hypotenuse together. Think back to SOHCAHTOA. SOHCAHTOA is CAH, cosine, cosine of the angle. Cosine of alpha is equal to 2 over 11. Cosine of alpha is 2 over 11, so take the cosine inverse of 2 over 11, and we get that alpha is about 79.5 degrees. From the 70-degree angle, 4 is the adjacent, x is the hypotenuse. That deals with the cosine ratio, so the cosine of 70 is equal to 4 over x. I want to solve this for x, which means that we're going to multiply both sides by x first, because I don't want x in the denominator. X times the cosine of 70 equals 4. Now to get x by itself, I'm not going to take the cosine inverse. Instead, cosine of 70 is a number. It can actually be evaluated. So we're going to divide both sides by the cosine of 70. So you'll take 4 divided by the cosine of 70. That can be done on the calculator. And we want to round this to the nearest hundredth. That comes out to 11.70. And it is a variable, so I don't have to put a label on it. 11.695 will round up, and to show that 0 is a significant digit, to show that we rounded to the nearest hundredth, that's why we want to put that 0 in there. So 11.70 for that one. If I look at my drawing, that seems to make some sense. X is the hypotenuse. It's got to be bigger than that little 4 in there. This one we have triangle ABC. It says angle A is equal to 90 degrees, so we'll draw the right triangle in there. Here's angle A. Here's angle B. Here's angle C. Angle A I know is 90 degrees. It says little b equals 5. Little b equals 5. That means that the side opposite of capital B, opposite of angle B, is equal to 5. So this length down here is 5. Segment AC is another name for segment, or for the variable little b. Little c equals 8, so opposite of angle C, that length is 8. That's what that first notation means. Then it says to solve the triangle means find everything. In this triangle, we have capital A, capital B, capital C. We also have little a, little b, and little c. We know that angle A is 90 degrees. We know that little b is equal to 5, and we know that little c equals 8. This is given to us. So we're just going to write down those numbers. We weren't given little a, we weren't given angle B, and we weren't given angle C, so I'm going to underline those just to indicate that these are the answers. These are the unknowns. The first three are locked in stone. That's what they are. Now we're going to calculate the other ones. To start off with, we're going to find little a. It's a right triangle. We have two of the legs. So to find the hypotenuse, which is little a, we can use Pythagorean Theorem. 5 squared plus 8 squared is equal to our hypotenuse squared. That comes out exactly equal to the square root of 89. We, however, want to write down an approximate number for this one because we're looking towards our answer. And we'll say that A is about 9.43. So now we have all three sides of the triangle, and we just have to find the two remaining angles. Square root of 89 is exact, so if I wanted to, I could continue to use that number. 9.43 is approximate, so I can't use that number in any future calculations, though. So it's written down as an approximate. It's a dead end. Don't ever use any rounded numbers. Now to find angle B, I'll go back to the two numbers we were given from the beginning, those two exact values of 5 and 8. Relative to angle B, 5 is opposite, 8 is adjacent. Opposite and adjacent deal with the tangent function, so I could say that the tangent of B is equal to opposite over adjacent, 5 over 8. I want to find the angle. I want to get B by itself. So if I think about algebraically, to get capital B by itself, we don't divide by tangent. That wouldn't make any sense. No, we take the tangent inverse of both sides. When you take the tangent inverse of the left, that simplifies down to just B. Take the tangent inverse of the right, the tangent inverse of 5 over 8. And that gives you that B is approximately 32.0 degrees. And 0 is a significant digit. Make sure you put that 0.0 in there to show that it was rounded to the nearest tenth. To find angle C, we have a couple of options. We could, from angle C, say that the tangent of C is equal to 8 over 5, take the tangent inverse of that, or realize that the 32.0 that we wrote down is rounded. I don't want to use that, but the number that's still in my calculator is still exact. I don't want to do 90 minus 32.0. Instead, I'll do 90 minus second answer. It'll keep all those decimal places in there. And in this problem, it might not make a difference. In other problems, it will. So make sure that you know how to use the answer function built into your calculator. And when you evaluate this one, you do get 58.0 degrees. It's showing up as 57.99461679. And there's other decimals that aren't showing. And if we had to use that number for something else, we'd want to use the exact that's still in the calculator that we can't even see because it doesn't show all the decimal places. But as our goal is to write down angle C, that is our best approximation to the nearest tenth of a degree. Okay, so here's the ground. Looking down at an angle of depression of 80 degrees. We always measure the angle of elevation and depression from the horizontal. So here's a horizontal line, and we'll just say Greg is a little bit shorter. Here is his shoes. Looking down at his feet, down at his shoes, this is our angle of depression of 80 degrees. So here's the start of our triangle, and my eyes are 70 inches off the ground. I could measure that over here on the left where I'm actually standing, or horizontal line going straight down there. That is also going to be 70 inches above the ground. We measure height vertically. The angle of depression is measured from a horizontal line. In other words, horizontal and vertical are perpendicular to each other. So we have this right triangle with an 80-degree angle, and this length is 70 or 70 inches. How far away is Greg standing? Well, that distance on the actual drawing would be this length across the bottom, though. That length is equal to this length across the top. So that X really stands for what we're trying to solve for in this one. If I put this all together, it's a right triangle. I have a side, I have an angle. I'm going to use trig. from that 80-degree angle, 70 is the opposite, x is the adjacent. Opposite and adjacent go back to the tangent function. The tangent of 80 degrees is equal to the opposite divided by the adjacent. So there is the actual trig function. Do some algebra on that. Multiply both sides by x to get x out of the denominator. Divide both sides by the tangent of 80. So x is 70 over the tangent of 80. There is an exact answer. We're going to then calculate that, and it comes out to about 12.34 inches. In the original problem, there was no x. So I'm not looking at a variable here so much as I'm looking at a distance. How far away is Greg standing? He's approximately 12.34 inches away.